We're on. Okay, guys, so today I want to talk to you about logical reasoning and counterexamples. Those two terms, I hope you have heard them from somewhere. Have you ever heard those two terms ever in your life? Or maybe this is the first time you're hearing it? Okay, well that's fine. Don't worry about it. We're going to talk about it anyway. The first thing I want to talk about is logical reasoning. What does it mean to be logical in a sense? What does it mean?
Makes sense.
It has to make sense, right? And when we apply this to math, there is a specific statement in math that represents logical reasoning. And we call this conditional statement. It's called conditional statement, and just like your language art class, there's a specific structure to the statement. This structure happened to be in the if and then form. Always in the if and then form. Now, in the if form, after the word if, is what we call the hypothesis of the conditional statement. Who knows what a hypothesis is?
An educated guess.
An educated guess, very good. And of course, right after the word then, we'll have a conclusion. Okay? Now, how do we recognize when we have a hypothesis or a conclusion? Well, based on this particular lessons right here, it's very easy. All you have to do is to put every event on a timeline, and then recognize which one happens first, which one happens later. So, for instance, let me give you an example. If I ace my test, then my parents will, well, you can put it in, you fill in the blank yourself. Your parents will what?
Award me.
Award you with something. Fine. But notice, for your parents to award you something, you have to do what?
Do something good.
Ace your test, right? So something has to happen first before something else will come. This is like cause and effect in your language art class. Something has to happen before the result comes, right? And how do we recognize that here? In this case, the hypothesis is the first event. And of course, your conclusion is your second event. So it has to happen after the hypothesis. It will always be written in this format. Even if it's not written in the if and then form, you can still rewrite it into an if and then form. What do I mean by that? Well, for instance, let me just give you one right here.
Can you write that down? Of course.
Just listen. Just have to note out for you're not writing it yet. Okay, read this one right here. If it rains, then I will stay home. Tell me, which event happens first? The rain has to happen first. Then if it rains, you stay home. Tell me, where is the hypothesis of this sentence? Yes? It rains, right. So what you do is you circle and say, that is my hypothesis. Where's my conclusion?
Stay home. Stay home. Stay home.
I will stay home, right? So the part that happens right after the word then. So here's the part, the conclusion part, and you label it. So if it's written in the conditional statement form or the if and then form, it's easy to identify. If, hypothesis, then, conclusion. That's easy, right? What if I don't write it that way? What if I write something like this? Let me see. Read the sentence, goes to the movie. Okay, look at this sentence. It's not written in the if and then form, but there is a hypothesis and there's conclusion right here. All you have to do is figure out which event happens first. Which has to happen first before something else will follow? Yes, what do you think? So you're saying that she doesn't have homework, have to go first, right? And then what happens if she doesn't have homework? Then she goes to the movie. You see, it makes perfect sense. This is why we call logical reasoning. You have to kind of just think about it. What happens first? What happens next? So once you have identified, you go and say, okay, so she doesn't have homework is your hypothesis or conclusion? Hypothesis, and then Kelly goes to the movie is your conclusion. Now you have the hypothesis and conclusion, and if I want you to put it back into the if and then form, how do you write that into the if and then form? Remember, if follows by what? Hypothesis. And where's your hypothesis here? Hypothesis here. Okay, so if she doesn't have homework, or if Kelly doesn't have homework, I'm just going to short that for a minute. Then what? Then she goes to the movie. Right. So notice, even if it's not already written in the if and then form, I want you to identify the conclusion and hypothesis. It shouldn't be that hard, right? That's all we're doing. Any questions so far in logical statement? Logical reasoning, anyway. We're good with that? So how do we form a conditional statement again? Using what form?
If and then.
If and then form. What happens right after the word if? Hypothesis. And after the word then will be your what? Your conclusion. Very good. Easy stuff. Okay. All right. Moving on. Next one I want to talk about is deductive reasoning. Now, do you know what deduction means? Yeah. What does it mean to you? Oh, good. Go down. That means you start with something big and you go down to very specific, right? So in mathematics, what does it mean? It means this. It means that you start with something very general, like a general rule, and then you deduct that rule and arrive to a very specific valid conclusion using that rule. So you basically use that rule as a guide, and then you try to find a valid conclusion out of that, if you can. If you can. I'm not saying it's absolutely a must, right? Sometimes you can't arrive to a valid conclusion. And I'll show you that case in a minute. But let me give you an example right here. Let's see if we can actually figure this out. For instance, here's a conditional statement. If the last digit of a number is 0 or 5, then the number is divisible by 5. Look at that conditional statement. Is that true?
Yes.
Any number that ends in 0 or 5 will always be divisible by 5. If you look at the 5 times table, what do you notice about all the digits in that table? It ends in 5 or ends in 0. So based on this conditional statement, is that true?
Yeah.
This is a general rule applied to any number that ends in 0 or 5, right? Can you give me a specific example to prove it? 25. Yeah. 25 works because, first of all, it ends in 5. And is it divisible by 5?
Yeah.
It is. It's 5. Anything else you want me to prove? Yes. 10, yeah. 10 ends in 0. Is it divisible by 5? Indeed. These are specific examples because you're just using deductive reasoning logic. Okay? You just prove that, hey, based on this rule right here, any number that ends in 0 or 5 will be divisible by 5. Okay? So let me just give you something here and see if you can still come up with a valid conclusion based on that. So for example, here's the first one. The number is 120. Is that true? Is that still true based on this conditional statement?
Yes.
Yes. Why? Because this number it's ending in what? 0. And of course, if it's ending in 0, it will be divisible by 5. So this is true. What about this statement right here? The number is a multiple of 4. Will this be true?
No.
Why? If a number is multiple of 4, give me a number that is multiple of 4. 16. Is 16 divisible by 5?
No.
Of course not. So because of that, this statement is false.
Wait, what?
120.
But will it work all the time?
No.
See? It says here any number that is a multiple of 4 should work too. Right? But that's not the case all the time, right? You can have 16 You can have 24, right? It still doesn't work. I know you can just isolate it. Well, what about 20? But that's an isolated case. When I say any number that's multiple of 4, it should be any number, not just 20. Does it make sense? Okay. Here's the next one. What about this one? Will that work? Based on my conditional statement?
No.
Does it follow the conditional statement? No. And you know very well that 101 doesn't end with 0 or 5. Therefore, it's not divisible by 5 either. So this is also a false. Okay. Any questions? What we're just doing right here, guys, is we're using deductive reasoning logic. I have a conditional statement. I'm giving out a specific example to prove it, whether it's false or it's true. Question? Okay, good, good. Last one I want to talk about is called counterexamples. So what are counterexamples? What do we use counterexamples for? Well, let's take a look at this one. I forgot the word then. There. So here's a sentence. If Susan is in school, then she is in math. What's wrong with that conditional statement? Can you find any error in logic? Yes.
She's not always in math.
Huh?
She's not always in math.
Exactly. She is not always in math. It doesn't mean that when you go to school, you will stay in math the whole day, right? What else do you have to go to? Thank you. There's so many other subjects to go to, and all you have to do is, for you to disprove this, meaning make it false, just give me one example. Susan can be in PE. So you just say, hey, Susan can be in PE while she's still at school, right? This statement right here disproves that because she doesn't have to be in math the whole day. This one right here, that what you just wrote down, is called a counterexample.
Counter-argument?
Yes, there it is. You're just trying to make a case, right? That's not true all the time. Here's my case. There it is. You see it? She's not in math all the time. She can be PE, she can be in history, she can be in science. Let me see if you can actually come up with another counterexample for this one. Check this one out. Okay, so what is wrong with this statement? Yes, Simon.
You don't always make something.
Why?
You could move.
Exactly. I could move.
Right?
For example, some of you might move to LA, right?
Oh, what if it's true?
Or whatever. But this right here that you just wrote down is your counterexample. Remember, when you declare something as being true, it has to be true 100%. You cannot, find a counterexample for it. For example, when I say 2 plus 2 is always 4, is that true all the time?
Yes.
See, for those of you who's brave enough to say, Mr. Nguyen, I have a counterexample for that, prove it to me. 2 plus 2 equals to 4. If you have something else, 2 plus 2 equals something else, yeah, that's called counterexample. But in this case, it is true 100% of the time.
No.
What?
Fish.
What? No, mathematically speaking,
Oh.
2 plus 2 is always equal to 4, right? Is that true? Okay, so there you have it. So, but as long as you can find a counterexample to disprove it, it makes it invalid. This whole conditional statement right here is invalid. Okay? Let's see if you can actually get this one. One last example here. If a quadrilateral four right angles, then the quadrilateral, I'm just going to shorten that, is a square. First of all, what is a quadrilateral? Yes.
The 4-sided figure.
Four-sided figure. Very general. Quadrilateral means a four-sided figure. Based on this conditional statement, it says if it's a four-sided figure that has 4 right angles, we all know what right angles are, right? 90-degree angles. Good. Then it's automatically a square. Is that true? 100% of the time.
Yeah.
Yes. Why not?
Because you could have a rectangle.
Exactly. Because a square, even though, yes, you're right, you have 4 right angles in there, a rectangle happens to be a quadrilateral that has 4 right angle in there too. When you say something like this, that is your counterexample. Okay. Any questions on what we covered today? Is this hard?
No.
No, it's not. So this is how we've concluded, guys. We are officially done.